you might think our sun is pretty big, and fair enough, it is. With a radius of 700,000 kilometers, the Earth would fit 109 times across the sun's diameter. Think of it this way. If the sun were a football, Earth would be the size of a tiny peppercorn next to it. Even if you took every planet in the solar system and mashed them together, the sun would still be over 700 times heavier. But here is the humbling truth. When it comes to the galaxy at large, our sun is nothing special. It's average. Even our closest neighbors show us up. The Alpha Centauri binary stars are roughly the same size as the sun, and Sirius A is already twice as big. We are small fish in a very, very large pond. So, how big can a star actually grow? And what if there's one so massive it could swallow our entire solar system, planets and all, and still have space left? First, let's look at how stars live and die. Let's look at stellar evolution. It all begins with a simple chart called the Hertzsprung-Russell diagram. It sounds complicated, but it's actually just a map. It was invented independently back in the early 1910s by two astronomers, a Dane named Ijnar Hertzsprung and an American named Henry Norris Russell. They realized that if you plot stars based on their temperature versus how bright they are, a pattern appears. Running right down the center of this diagram, like a spine, is a line of stars called the main sequence. This is the comfort zone. This is where most stars spend the majority of their lives. If a star is on this line, it means it is stable. It has already survived the chaotic, violent collapse of the gas cloud that birthed it. Now it is just doing its job, continuously fusing hydrogen atoms in its core. This fusion creates a massive amount of energy that pushes outward. At the same time, the star's own gravity is trying to crush it inward. It's a cosmic tug-of-war. When the push of the energy balances the pull of gravity, the star reaches a state called hydrostatic equilibrium. It's a fancy way of saying the star is stable. It is at rest. Almost every star on that main sequence line is in this state of balance. But just because they are all balanced doesn't mean they are all the same. Far from it. Our sun sits comfortably right in the middle of this diagram. It is what astronomers call a G-type main sequence star. Now, that letter G is part of a classification system. Scientists sort stars by their temperature, which also determines their color, using a seemingly random string of letters: O, B, A, F, G, K, and M. O stars are the hottest and bluest. M stars are the coldest and reddest. The sun, along with other G-type stars, has a surface temperature of around 5,778 Kelvin. That specific heat gives it the yellow-white color we see every day. Deep inside its core, it is a fusion factory. It converts about 600 million tons of hydrogen into helium every single second. That energy radiates out and, in our case, it has been powering life on Earth for billions of years. But if you start moving up or down that main sequence line, the stars change dramatically. A pattern emerges. It's probably not surprising to hear that the dim stars are usually cool. And, logically, the hotter a star gets, the brighter it gets. That makes sense. But what is less intuitive is how a star's weight, its mass, relates to all of this. There is a clear link here. The brightest stars also tend to be the heaviest ones. Let's look at a specific example to make this clear. Look at the constellation Orion. The star that marks his left shoulder is called Bellatrix. It is the 26th brightest star in our sky. Bellatrix is a B-type star, which puts it near the top of the brightness class. Its surface burns at a scorching 22,000 Kelvin. That is almost 4 times hotter than our sun, but more importantly, it is 8.6 times more massive. That extra mass changes everything. Because Bellatrix is so heavy, gravity is crushing its core with incredible force, far more than what our sun experiences. This immense pressure cranks up the fusion reactor in the center. The reactions happen faster, harder, and more violently. This fusion is so powerful that it forces the star to physically swell up. It is as if gravity can barely contain the explosion happening inside. Because of this, Bellatrix has a volume that is a whopping 200 times greater than the sun, but living this large comes at a terrible price. Massive main sequence stars are like rock stars. They live fast and die young. Our slow, steady sun will likely live for a total of 10 billion years. Bellatrix? It has been burning for only 25 million years, and it is already running out of time. It probably only has about 7 million years left before it dies. Because they die so quickly, these large stars are actually quite rare. We're simply less likely to see them compared to the smaller, longer-lived stars that hang around for eons. So, does that solve the puzzle? If we want to find the largest star in the universe, should we just look for the heaviest one? Not exactly. It is generally thought that stars can't get much heavier than 150 times the mass of the Sun. If they get heavier than that, the energy inside becomes so intense that the star literally blows itself apart. It becomes too unstable to exist. However, the universe loves to cheat. It has found ways to bypass this limitation. Occasionally, two massive stars will crash into each other and merge. When they combine, they create a true abomination. A star far larger than anything that could form naturally from a gas cloud. This violent merger process is likely the explanation for a star with the exciting name of R136A1. This thing is potentially the most massive and most luminous star in the entire known universe. On our map, the Hertzsprung-Russell diagram, R136A1, sits at the furthest, most extreme top left point. It is a monster. Forget that limit of 150 solar masses. This beast is estimated to be 265 times the mass of our Sun. In terms of size, it has a radius 40 times wider than our star. R601 is part of a very exclusive club known as Wolf-Rayet stars. They are incredibly rare. We have found only about 220 of them in our entire galaxy, though scientists think there might be a couple of thousand hiding behind dust clouds. These stars are massive, and they are in a very advanced, very short phase of life. They are essentially knocking on death's door, waiting to collapse into a supernova explosion. Because they are so unstable, they are constantly falling apart. They throw off vast amounts of plasma and powerful winds. One ejects as much as 10 solar masses of material every million years, blasting it out at speeds of up to 3,000 kilometers per second. They are also blindingly bright. In just 4 seconds, R136A1 releases as much light energy as our Sun produces in an entire year. Think about that. 4 seconds equals 1 year of our Sun's output. However, if you looked at it, it wouldn't look that much brighter to the naked eye, only about 164,000 times brighter, because most of its deadly energy is blasted out as ultraviolet light, which we can't see. To be honest, we are incredibly lucky to have seen this star at all. It will likely only exist for about 3 million years total. In the timeline of the universe, that is the blink of an eye. But here is the twist. Despite all that weight and power, R136A1 is not the largest star in the universe. Not by size. It is certainly the heaviest, but there are stars that weigh much less but grow much, much larger. How is that possible? It turns out the very largest stars have a trick up their sleeves, or rather, in their outer shells. Up until now, we have been talking about main sequence stars, the ones that are burning hydrogen in their cores. But eventually, that fuel runs out. When the hydrogen tank hits empty, the explosive energy of fusion stops. Without that outward push, the star's intense gravity wins the tug-of-war, and the core starts to collapse inward. This collapse creates massive pressure, which turns up the heat in the core once again. Eventually, it gets hot enough to start fusing helium, which saves the star for a moment and kicks it into a brand new phase of life. But this new heat does something else. It warms up the outer shells of the star. These outer layers reach temperatures that used to only exist in the center. Suddenly, the leftover hydrogen in those outer layers ignites. This causes the star to expand dramatically. It balloons outward, transforming into a red giant. This is the fate that awaits our own Sun. Right now, our radius is 700,000 kilometers, but when this death process begins, the Sun will expand to a diameter of 300 million kilometers. It will grow big enough to consume the orbit of Mercury, then Venus, and possibly even the Earth itself. This terrifying expansion happens in stars that are anywhere from 0.8 to 8 times the mass of the Sun. A great example of a red giant we can see right now is Mira A in the Cetus constellation. It's not very heavy, only about 1.2 times the mass of the Sun, but because it is dying, its radius has ballooned to at least 332 times that of the Sun, and Mira A is unstable. It pulses. It breathes. Over cycles lasting hundreds of days, it physically puffs up. At its maximum size, it can reach around 402 times the radius of our Sun. But incredibly, even a red giant isn't the biggest type of star. If you start with a heavier star, something over 8 solar masses, you get a different monster. You get the Red Supergiant. These are the true titans. They are towering, mighty, and vastly larger than their smaller cousins. They are also doomed. These monsters will end their lives in a catastrophic supernova explosion, but right before that end, in the final moments of their lives, they swell up to become the largest objects in the cosmos. Betelgeuse is one of these famous monsters. It has a diameter of 1.2 billion kilometers. That makes it more than 700 times the size of the Sun. If you replaced our Sun with Betelgeuse, all the rocky planets, Mercury, Venus, Earth, Mars, would be instantly engulfed. Even Jupiter wouldn't be safe. These supergiants are violent beasts. In the final death throes of their lives, they pulse and throw out huge amounts of gas and dust. This creates a messy, hazy fog around them, which actually makes it difficult for scientists to say exactly where the edge of the star ends and where open space begins. But despite its enormous size, we know that Betelgeuse is not the king. There is one other candidate. As I hinted at the very beginning of this journey, it is lurking in the constellation Scutum. This is UY Scuti, and large doesn't even begin to describe it. It is colossal. It is so vast that you could fit 5 billion suns inside of it. Let that sink in. 5 billion of our suns. Surprisingly, for all its size, it isn't very hot. In fact, it is about 40% cooler than our Sun. It glows with a somber, deep red color. It is the ultimate red supergiant. Because it is so far away and relatively cool, you can't see UY Scuti with your naked eye. You need powerful binoculars or a telescope to spot it in the dark. It sits at a distance of 5 to 10,000 light years from Earth. Because of that distance, there is some uncertainty about its exact measurements, and there are other stars that constantly challenge it for the title. But UY Scuti won't be around forever. It is already 10 to 20 million years old. It may only have a few million years left on the clock. Within that time, it might actually get smaller. It could transform into something called a yellow hypergiant. This class of star is incredibly bright, but to get there, UY Scuti would have to shed its outer layers. It would need to blast them off into space to expose the hotter layers underneath to keep the fusion reactions going. These hypergiants are volatile. They are capable of blowing off the mass of the planet Jupiter in just one explosive burp. And they burp often. This might sound destructive, but it is actually beautiful. These ejected materials are filled with heavy elements like oxygen, carbon, and nitrogen. They form vast clouds of dust that stretch for 10,000 astronomical units. That is 300 times the distance from the Sun to Neptune. These clouds are vital to the development of the universe. They mix with other dust and gas, creating stellar nurseries. They provide the ingredients for new stars, new planets, and eventually life itself. This transformation is still a long way off for UY Scuti, maybe hundreds of thousands of years away. But there is another giant star that is even closer to this final act. We have only ever properly imaged one star outside of our own Milky Way galaxy. It was a star called WOH-64, a red supergiant very similar to UY Scuti. It lives 160,000 light years away in the Large Magellanic Cloud. Recent studies suggest it might have already turned into a yellow hypergiant. In just the last 10 years, it has become dimmer, which suggests it is throwing off material and burying itself in a shroud of dust. The problem is, at these extreme distances, it is incredibly hard to measure things precisely. Maybe WOH-D64 is actually bigger than UY Scuti? We just don't know for sure. We also don't know if stars can get any bigger than this. It seems unlikely. Giants like UY Scuti are scraping the edge of a theoretical barrier called the Hayashi limit. This is a line on the Hertzsprung-Russell diagram that represents the maximum size a star can reach given its mass. If a star tries to cross this line, the physics inside changes. Convection takes over, gravity starts to win, and the star is forced to shrink back down. We may one day come across a star slightly bigger than UY Scuti, but it won't be a significant difference, unless there's something we've completely missed about the nature of the universe. Maybe there's a type of massive star we haven't yet discovered in our galaxy. But, for now, we just don't know, and our technology isn't advanced enough to figure it out. What's certain, though, is that as humans, our minds struggle to fully grasp sizes beyond a few thousand kilometers. The enormity of these stars is far beyond our understanding. They're like cosmic beasts, dwarfing anything we can imagine. And yet, even these colossal stars are just specks in the grand scheme. Galaxies stretch across tens of thousands of light years, and they are separated by millions of light years. Vast networks of the cosmic web span billions of light years. The universe is so enormous that our comprehension falls short. But just because we can't wrap our heads around it, doesn't mean we shouldn't try. And perhaps it's a good thing that we live on a small, unremarkable planet, orbiting a star that isn't much different from the countless others out there. Maybe that's exactly what we need.